Welcome to the team. I know you've got your Network Plus foundation down, which is awesome. But today, we're stepping off the textbook pages and into the real world of enterprise networking. Think of me as your senior network architect, and together, we're going to tackle your first major data center deployment. In this explainer, we're taking your skills straight to the Cisco CCNA level by mastering the art of configuring and verifying switch interfaces.
But before we start configuring things, let me paint a picture of a very real, very frustrating scenario that you will absolutely face out there in the job market. Picture this. You've just plugged a critical new server into a massive corporate Cisco Catalyst switch. You check the physical port, and hey, the link light is a beautiful, solid green. Everything says it's connected. But when users try to access the server, the network is inexplicably crawling. I mean, it's dropping packets, it's lagging, it's honestly performing worse than a 1990s dial-up connection. Why? Well, stick with me, because by the end of this, you won't just know the answer to this mystery, you're going to know exactly how to fix it.
Okay, so here's our roadmap. We'll start with our data center mystery, move to controlling port power, setting speed in duplex, navigating the auto-negotiation trap, reading interface status codes, and finally, solving our network mystery.
All right, Section 1, a data center mystery. Let's set the scene.
Okay, let's just dive right in. This right here is the physical reality of our job. We're talking miles of unshielded twisted pair cabling, racks upon racks of servers, and incredibly dense Cisco Catalyst switches. Now look, anyone can plug a cable into an RJ45 port until it clicks, right? But as a network architect, our job goes way beyond the physical layer. Our job is to make absolutely sure those physical connections translate to flawless, high-speed logical performance. And honestly, the very first step in doing that is taking absolute control over the switch interfaces themselves.
Which brings us to Section 2, controlling the port power. Let's take command. So, to take control of our interfaces, we need a way to turn them on and off without, physically walking into a freezing server room to pull a cable. Cisco gives us two oddly named but literally essential command line interface commands for this. They're shutdown and no shutdown. Think of these exactly like the main electrical breaker switches in your house. When you issue the shutdown command in interface configuration mode, you're throwing the breaker. You are administratively disabling that port. To flip the breaker back on and enable the interface, you just issue the no shutdown command. You are going to use this so often, it'll become second nature to just type shut and no shut.
Now, what's really interesting is what actually happens behind the scenes here. When you shut down a port, the switch doesn't just do it silently in the dark. No, it generates a syslog message directly to the console. If you look at the output, notice how the interface state changes to administratively down. This right here is your definitive proof that the port is disabled by a human's configuration, not by some broken cable or hardware failure.
Moving on to Section 3, setting speed and duplex. Let's go over the rules of the road.
Right, so speed and duplex dictate exactly how data flows through those ports we just powered on. To manually set these, we follow a very structured workflow in the Cisco CLI. First up, we enter global configuration mode by typing configure terminal. Then, we drill down into the specific port we want to control. Let's say interface fast Ethernet 0/1. Once we're in interface mode, we can explicitly set the speed, like speed 100, and set the duplex, like duplex full. It's a really logical progression when you think about it. You go from the whole switch, down to the specific port, and finally down to that port's specific behavior.
And this brilliantly illustrates what the word duplex actually means, because honestly, it can be a kind of confusing piece of jargon. Think of half duplex like a narrow, one-lane bridge. Cars can travel in both directions, sure, but they absolutely must take turns. If two cars try to cross at the exact same time, you get a crash, or in networking terms, a collision. The devices literally have to back off and try again. Full duplex, on the other hand, is a multi-lane, two-way superhighway. Devices can send and receive data simultaneously without ever worrying about colliding. So in the real world, modern networks should almost always be operating as that full duplex superhighway.
Let's hit Section 4, the auto-negotiation trap. Time to uncover some hidden dangers. Out of the box, Cisco switches default to speed auto and duplex auto. This means they use a process called IEEE auto-negotiation. Think of auto-negotiation like two foreign diplomats meeting in a room trying to automatically agree on the best shared language to speak. Most of the time, this works beautifully. They shake hands, they agree on a gigabit speed in full duplex, and data flows perfectly. But what happens when one of those diplomats refuses to negotiate? Well, suppose a PC user, or maybe a server admin, decides they want to force their network interface card to 100 megabits per second and full duplex. By hard-coding those settings, they completely turn off their device's auto-negotiation. Our Cisco switch, meanwhile, is still sitting there with its default auto settings, trying to talk to a device that has suddenly gone completely silent during the negotiation phase.
So the absolutely crucial point here is how the switch reacts. When a Cisco switch's auto-negotiation fails to hear back, it just falls back to IEEE defaults. It can usually sense the speed electrically, so okay, it matches the 100 megabits. But for duplex, the standard actually dictates that for 10 or 100 megabit speeds, it must fall back to half duplex. The result of this, the duplex mismatch disaster. One side is operating as a cautious one-lane bridge, carefully listening for collisions, while the other side is acting like a superhighway, blindly blasting traffic at full speed at all times. It is a mess.
Section 5. Reading Interface Status Codes. Here is how we go about finding that mismatch.
To spot these hidden problems in the wild, we rely heavily on the Show Interfaces command, which gives us two critical status codes. Our cheat sheet here breaks this down perfectly. The first code is line status. This is layer 1, the physical hardware. Basically, is the cable actually plugged in? The second code is protocol status. This is layer 2, the data link logic. If you see administratively down/down, you know someone used the shutdown command. If you see down/down, well, you likely have a bad cable or the device is just turned off. But what we really want to see is up/up, meaning both the physical link and the logical protocol are working normally.
But guys, here is the really tricky part about a duplex mismatch. The interface will actually show as up or connected. The lights will literally be green. So to find the mismatch, you have to dig deeper. You use Show Interfaces status and you look for the A- prefix. If one side says A-full, meaning auto-negotiated full, and the other side just says half, boom, you have a mismatch. Furthermore, if you check the interface counters, a mismatch is going to reveal itself through a rapidly incrementing collisions counter, and most importantly, late collisions. Late collisions are the ultimate forensic proof that our two diplomats failed to communicate properly.
Finally, Section 6, Solving the Network Mystery. Let's tie it all together.
Remember our sluggish server from the beginning? The one with the solid green link lights? Well, we check the connection, the cable is totally fine, we run our Show Interfaces command, and the port is happily up/up. But when we look at the statistics, we see thousands of late collisions. We investigate the server, and boom, there's the answer. The server administrator hard-coded the server's network card to 1000 megabits full duplex, completely disabling auto-negotiation. Our switch, left on its default auto settings, fell back to the IEEE defaults, resulting in a catastrophic duplex mismatch.
The fix for this is brilliantly simple, but it requires strict discipline. You must always match your configurations on both ends of the link. You essentially have two choices here. You can either tell the server administrator to change their NIC back to auto-negotiate so both diplomats can talk again, or you go into your Cisco switch CLI, enter interface configuration mode for that specific port, and manually issue the commands speed 1000 and duplex full. Once both sides match perfectly, the collisions stop and our server is back to running at lightning speed.
So to wrap this explainer up, here are your golden rules for success, both on your CCNA exam and out there in the real job market. Number 1, always verify your physical layer 1 cables first. Number 2, ensure the port actually has power by verifying it isn't administratively down. 3, ensure your speed and duplex settings match perfectly across the link to avoid that auto-negotiation trap. And 4, trust your Show Interfaces status and counter commands to reveal the truth even when those green lights are lying right to your face.
I want to leave you with a final thought to test your new mastery. What if you check an interface, it says up/up, there are absolutely no collisions, but your input counters are just racking up thousands of CRC errors? Well, if it's not a duplex mismatch causing collisions, a rising CRC counter usually points to severe electrical interference on the physical cable itself. Maybe somebody routed it too close to a heavy power generator. Networking is always kind of like a giant puzzle, but with these tools in your belt, you are now ready to solve it. Thanks for joining me on this explainer, and I'll see you in the data center.